It's my pleasure to welcome Professor Bruce Maggs from Duke University, who is the world's expert on performance engineering for networks of any kind, whether it be internet or networks in your processor or whatever, but mostly he's been looking at internet related things because after all, internet is pretty big. With that, let me, Bruce, why don't you share your screen and.
Okay, can you see that?
Yes.
All right, now, but before I share, I'm a little disappointed, Charles, that you spilled the beans about your birthday because we have already been conspiring against you.
Oh, no.
Although this will be very painful and may go down as a bad idea in 6172 history, I am now going to lead the class in a rendition of Happy Birthday. A 1 and a 2 and a hit it. Happy birthday to you.
Happy birthday to you. Happy birthday, dear Professor Charles. Happy birthday to you.
Okay, so yeah. Happy birthday, Charles. That was truly horrible. I'm hoping that was just the students messing with us, but if not, it's fantastic motivation for the last third of my lecture. So it's great to be back. I co-taught this course in fall of 2019. And I know most of the course is not about networking performance, but that is another important aspect of performance engineering in many contexts if you really want to make things work well. And last year, Charles asked me to prepare a lecture talking about different ways to squeeze performance out of your network. I think I'm also following on Slack, so if you have questions, ask me, and if I don't respond, maybe a TA could just interrupt me and let me know. Or you're free to interrupt me too. I handle questions well. Let's start. How can you speed up the network? Well, first thing you can always think about is maybe we don't need to use the network. We're so accustomed these days to having resources on demand, say in the cloud, that we sometimes fail to appreciate just how much computing power we often have at our fingertips. Here's a screenshot of the inside of my laptop. And it's really, especially when you think back to what we envisioned computers being like 20, 30 years ago, it's a supercomputer. And yeah, my laptop weighs 13 pounds, but it's got 2 graphics cards and 3 fans in it. And it's just amazing what I can do on the laptop itself. In fact, it reminds me of the movie Ted and sort of the most powerful thing I have. I don't have an Apache helicopter, but this laptop is pretty darn close. That's enough about local computing though. Let's talk about what to do if you really have to use the network. One thing you probably learned from Project One was you should avoid copying data at all costs. It's basically wasted work. And the place where this comes up in the networking context is when you have data that is arriving from the network, it lands at a network interface card, and it has to get from there somehow to your program. And the standard way that this is done in Linux is that the data is first copied from storage on the network interface card into kernel space. And then, so that's a special area of memory that is reserved for the operating system. And then from there, your program can copy it into user space and read the data. And if you need to go the other way, the opposite copies have to take place. And it's natural to hope that you could somehow avoid doing all this copying. And so actually only fairly recently, we've seen improvements where you can do things like copy data directly from the storage on the network interface card into user space. That's nice. That gets rid of one copy. Or even more extreme, push more and more of the computation into the network interface card itself. There's certain things that are just done over and over and over again, like managing the bookkeeping details of a TCP connection, that it's not that hard to put into the network interface card. I'm not going to spend a lot of time today talking about network protocols, but TCP is the workhorse network protocol of the internet. It's the transmission control protocol. And it's used these days, still true almost all the time when you make a connection from a browser to a web server, or really from almost any client to any server, with a few exceptions. And TCP governs the rate at which you can send and receive data, and also takes care of making sure that if there are losses as you send data or corruption, the data gets resent until it's successfully transmitted. Here's another thing you could do. You can try to find something else to do while you're waiting for the network. And in your code, there are a couple ways you might do this. So one thing you could do is use a non-blocking socket. Now, in Unix programming, in C or C++ programming, the traditional way to interface in software with the network was to create something called a socket, and then to read and write data to or from that socket. And the normal socket calls are blocking, so that if I call a read or a receive, my program will wait until the network has some data for me to read. But it doesn't have to be that way. You can set the options on your socket and tell it, I'd like this socket to be non-blocking. And what that means is that if I issue a read and there's no data, I'd like the read to return immediately and just tell me there's no data, so I can go about doing something else and come back to it later, try again if I still need the data later on. So this is how you would implement this in C. And this is simple code, a little ugly. By the way, socket programming is ugly, but it's the old-fashioned way. Nowadays, when you use other programming languages, there's often built-in support for higher level networking primitives. But in C, you're talking directly to sockets, and they're like pipes, and you're basically just reading and writing bytes into these sockets once they've been set up. Another way you could do something else while you're networking is to spawn a separate thread for each connection that you're processing. And this is a very common technique that a server might implement. And the idea is that you could listen and wait for a client to connect. And when you get a request to open a connection to a client, you could accept that request. And then once accepted, you could spawn a new thread and pass it the socket. And then that thread would deal with reading data from the socket and acting on it in whatever way is appropriate. This way, when there's no data to be read, the thread will just be idle, and other threads in the main thread of the program will be able to continue doing their work. Now, I've talked about accepting a socket here. And what I mean by that is, if this is a server like a web server and a client like a browser wants to connect, there's a little protocol that takes place with TCP where the client sends a request over to the server and asking to create a TCP session, which leads to the creation of a new socket. Okay, now here's one of my all-time pet peeves, and this one is not so much for you as the programmer, it's really, but although it could be, but it's more for the designer of network protocols, and that is one of the real keys to making the network run faster is to reduce the number of round trips. So I want to show you some tools that you can use to find out what's going on under the covers. One of the things I really love about 6172 is that you become familiar with all sorts of tools for analyzing what's going on under the covers with the execution of your code and helping you find things that are slow and that way you can address them. And I'm going to show you real quickly the number one tool for people who are interested in what's going on with their network. But first, let me introduce the internet service model. The typical user of internet services, and you guys are not necessarily typical users, but the typical user doesn't need to understand what's really going on under the covers. But there's a shared model, a shared service model that's called IP, the Internet Protocol. And it's really simple. It says, well, the network will do its best to deliver each packet to the destination address listed in its header. This is like pretty much the same thing as the US Postal Protocol. You put an address on a letter, you put a stamp in it, and you put it in the mailbox, and the post office will make a best effort to deliver it. So under everything, that's what the internet does. Everything else has to be built on top of that particular service model. And best effort means that it doesn't guarantee 100% of the time the packet will arrive. It doesn't say anything about how fast it will arrive. You need to figure out what to do when something goes wrong. That's where higher level protocols like TCP come in to try to help. But the main idea is that there's just two things going on. You've got an address, destination address you can stuff in a packet, and then the network tries to deliver the packet. So let's take a look at some protocols and see about this round trips. First, what I did when I created these screenshots is I went and found the IP address, the network address or internet address of my laptop. And this is really pretty easy to do. You can, on Windows, type ipconfig, and it tells me here that my IPv4 address is 152.3.136.127. And on Mac or Linux, you could use ifconfig or IP. And either way, you find out, okay, if someone wanted to send a packet to my address, what is that address? What would they use? Now, in this particular case, I was on Duke's Wi-Fi network, and it had given me a public IP address. There's some complicated things that sometimes go on with network address translation, especially when you're in a home network. But let's just, for simplicity, assume we're looking at a case where I'm on the public internet, and that's my address. Anyone can send a packet to that address. And I'm interested in connecting to the web server www.cs.duke.edu, because that is a location of my favorite homepage, which is www.cs.duke.edu/twiddlebmm. I spent a lot of time there. And so first thing, let's find out the address of www.cs.duke.edu. That www string is an example of a domain name, and it's meant to be sort of human readable or something humans can remember. But the IP protocol doesn't directly know how to send data to a name like that. There's a separate protocol called the domain name system that is in place and is used to translate these human readable names into network addresses. And if I'd like to translate that name, I can, on a Windows machine, I can type nslookup www.cs.duke.edu, and it tells me, oh, okay, the name server that I'm using to resolve that name is duke.cs.duke.edu, which is kind of a weird name. That doesn't make any sense to me, but fine. And it tells me that the name www.cs.duke.edu is actually an alias for another name, sybil.cs.duke.edu, which is, I don't know, getting a little creepy. And the address is 152.3.140.31. Now, normally you don't go through this step when you contact the web server. You're never going to type in 152.3.140.31. But I did it because I'm going to teach you how to use a tool in a moment. And I wanted to know the IP address of my machine and the IP address of the web server so that I could look at the packets going back and forth between them using the tool. The tool is called Wireshark, and it's a tool that lets you inspect the contents of every packet that your computer receives or sends. And one of the beautiful things about Wireshark is that a huge amount of effort has gone into incorporating in Wireshark the knowledge of hundreds of different network protocols, so that when it sees a packet, it can tell you in great detail what it knows about that packet. So in this particular instance, I'm running Wireshark on my Windows computer, but you can run it on Mac or Linux. And I went into my browser and I typed a request, HTTP. I guess I did this not securely, which was ill-advised, but nevertheless, worldwideweb.cs.duke.edu/twiddlebmm. And then in Wireshark, near the top where it says filter, I entered a logical expression telling it I'm only interested in looking at packets whose source or destination is either my laptop's address or the web server's address. And the reason for this is that these days there's a tremendous amount of traffic going in and out of your machine all the time, whether you even know about it or want it. And you have to add a filter if you want to only look at the traffic between your machine and some remote machine. And so I did this, and let's look at the first 3 packets in the upper left of the Wireshark window, not all the way at the top, but you see where there's a line that says number, time, source, destination, protocol, length, and info. First, under number, the first 3 packets are the ones of interest, 1202, 1203, and 1204. And 1202 is the first TCP packet that my browser sent to the server. And it has a flag, a 1-bit flag in its header that says SYN, which stands for synchronize, and basically says, hey, I'd like to open up a TCP connection so that we can start exchanging data. And the second packet, 1203, comes back, and it's sent by the server back to my browser, and it has 2-bit set in its header, SYN and ACK. SYN says, okay, I agree, let's synchronize. And the ACK says, yeah, I got your last packet, and here's the sequence number that I received from you. And then the third packet, 1204, that's my client sending an ACK back to the server saying, okay, I received your SYN packet. And this is called TCP's 3-way handshake. And after this is done, the 2 sides can start exchanging data. That's great, except that we had to go through these round trips before we could do any useful work. And a natural thing to ask is, hey, well, why couldn't I just start sending my data to the server in the first packet? Why not just go ahead and here I'm connecting to a web page. If you look at packet number 1221, you can see this is the last one shown. It says get/twiddlebmm http/1.1. Okay, at some point that's really what I want to send. I want to say, yes, give me this web page. But that's not what happens. First, we do this 3-way handshake to set up the connection. So let me ask the class, does anybody have any idea why that might be useful? Like what is the purpose of this 3-way handshake? Total silence. Okay, how about this? Can you guys still hear me? Am I still online? Make sure the server is accepting packets. Okay, so that's sort of true. Yes, I'm going to rephrase that, but at a high level, that's kind of true. What you're really trying to do is make sure that both sides can communicate with each other before you do anything. And now, it wouldn't have hurt necessarily that much from the client's perspective if it just sent the request and hoped for the best. But it's really done in part to prevent a certain type of attack where fake requests are sent to a server with spoofed or fake source addresses. So I told you the IP model was that you put the address of the destination in the packet. It turns out you also put the address of the source in the packet, and that's so if the destination wants to reply, it'll know where to reply. That's the return address. It's like in the postal model, it's like the little upper left-hand corner return address. The type of attack you might be worried about is where you send a server a packet with somebody else's address in the return address, and then the server starts sending data to that address instead. That might be some victim. And what you're really trying to do here is just send a server a little request and get it to start dumping a bunch of data at a victim. Oh, by the way, there's another good response about why we might do this handshake, about exchanging keys to encrypt data. You're anticipating my next slide. Unfortunately, that's going to just add more round trips. And yes, we are going to do that. But the exchange of keys doesn't happen in the TCP three-way handshake. So by requiring this handshake, the server knows that it can send a response, a very small response back to the return address, and get an acknowledgement from there before the two sides start doing any work. And so at that point, there's two-way communication established, and that's a lot harder for an attacker to fake if the return address isn't really the attacker's return address. Okay? There are other ways to stop spoofing attacks as well. Like in general, networks tend to block or drop packets if they exit the network, but their source or return address isn't within the network. That sort of seems just weird. It's like somebody driving down the road and sticking mail to be sent out into other people's mailboxes. It doesn't normally you don't do that. Okay, but yeah, there was a good question by Ayush, who said, what about exchanging keys so you can encrypt data? And the internet today is going to everything being encrypted, and the workhorse protocol is called SSL, or actually nowadays it's called TLS, but it's just the new name for SSL. We're on TLS version, I don't know, 3.1, I think, but this is a little explanation of how 3.0 worked. And after we have done the three-way handshake, if we were making a secure connection, then what would happen is the client, the browser in this case, let's call the client Bob, would send a message to the server called the client hello and say, I'd like to establish a secure connection within this TCP connection. I want a TLS connection. And here are the different cryptographic protocols that I understand. And then the server comes back and says, okay, great. Let's pick this one from the ones you understand. And here's the session ID. And by the way, here's my public key. And I'm not going to go into this, but this is something that the client can first try to verify that this really seems like it's a valid public key. And if it is, then the client can generate a private key for use in this session, encrypt it with the public key, and send that to the server. And this begins sort of the establishment of key exchange and the establishment of a secure connection, requiring additional round trips. And all of this is still happening before we actually do any work that really matters, like make the request, what web page do I want, and then get the response. So round trips just kill us. We'll talk a little bit about efforts that are being made to reduce round trips. Google has been a real leader in this area. We'll see how you might try to reduce both of the round trips that we've seen so far, the three-way handshake and the TLS session establishment. But here's another approach, which is, what about moving the data or the service closer to the user? I mean, at some point, there's no getting around the speed of light. If things are far away, it will take more time to get them delivered. And not only that, but there's just more things that can go wrong along the way. And so Charles didn't mention it, but over 20 years ago, I was also at MIT visiting Charles when I got sucked into another MIT spinoff called Akamai Technologies. And I was one of the founding employees and the first head of engineering at Akamai. And I'm going to tell you a little bit about what Akamai has done to speed up web performance. And the idea was to move the data closer to the users. So initially, Akamai came up with this new service, which is delivering the objects that appeared on web pages, like delivering pictures. And the pictures were most of the bytes. Those that at that time, especially the graphics in the pictures was most of the bytes that had to be delivered from the server to the browser. And Akamai went to content providers like CNN.com and said, hey, look, we can speed up your web page because we're going to put servers near to end users in the same networks as the end users. For example, there are, or at least there used to be, a bunch of Akamai servers on the MIT campus network. And whenever a user of one of those networks visits your page, they'll get the images from the nearby servers. And by the way, this will also reduce the amount of infrastructure that you guys have to buy and manage. You can just rent this capacity on demand from Akamai. You guys may have noticed Akamai has a beautiful brand new headquarters building, also 1 block away from CSAIL. So this is a big MIT success story. Okay, so why does reducing latency matter? Well, in the context of web pages, reducing latency is well known to increase sales, which is what really matters. So this is a graph showing for different types of client platforms, desktops, phones, or tablets, what's the conversion rate as a function of the page load time, which is a metric that roughly tells you, but very roughly, how long it took for a page to be rendered in the browser. And you can see that conversion rate is fantastic. It's a business term for did the person buy something. But to me, it's great. It sounds like a religious term, right? And if you want to convert someone, you got to do it fast. So it's showing here that if you can display the page within 2 seconds, you have a good chance, and good here means 2 to 3% of getting the person to buy something. But it drops off dramatically after that. And this is an Akamai study, so maybe take that with a grain of salt. But Amazon and Google and Microsoft and others have replicated this study in many contexts, such as how many search queries will you do? Well, it depends a lot on how fast the answers come back. Reducing latency translates directly to increased revenue. That's the big driver for Akamai's business. The other thing, though, is it's nice for these content providers not to have to invest in enough infrastructure to take on their peak loads. There are some content providers who have these very sort of occasional gigantic loads. So Fortnite is one of them, and they release a new version which they call, darn it, I forgot what they call Fortnite release. Hey Peter, what's a Fortnite release called?
I don't know.
Okay, anyway, a season. It's called a season. They call it Fortnite season. When a Fortnite season was released in this was 2018, it led to 37 terabits per second peak bandwidth for one day, and then it went away for Fortnite. And so one of the nice things about this new model in which you can outsource content delivery is that it also makes these resources more fungible. Having said that, of course, the content delivery network, the company like Akamai, knows that once the content provider stops building up their own infrastructure, they can never go back. They're hooked. Now it has to be done by somebody else because they don't have who has the resources to support a 37 terabit per second download. Let me show you really briefly the mechanics of how this offloading delivery of objects worked in the earliest days, and still to some extent it's the same at Akamai. So here's a fake web page for a website called xyz.com. And originally, the same server, www.xyz.com, was delivering both this HTML homepage document as well as the images that appear on it, a logo and a background image. But if they were to outsource delivery to a content delivery network, it could be as simple as just changing the domain name of the server that's going to deliver the objects and making another configuration change, which I'll show you in a minute, to their DNS. And so here, this is sort of the main technical slide of this whole lecture, but here's how Akamai DNS resolution works. So the users typed in www.xyz.com. That HTML document was fetched. The browser noticed, I've got to resolve these two new names, ak.xyz.com. What's one name, but I need it for two purposes. So it looks to see, have I cached that already? If not, it asks the operating system, can you use DNS to resolve ak.xyz.com to an IP address? Because I need to send a request to that web server. And the operating system, if it doesn't have it cached, will issue a query to its local name server. At MIT, I'm sure that, so I don't remember, it used to be probably called SITB. I don't know what it's called anymore, but like somebody runs the IT infrastructure that everybody shares at MIT. And I'm sure that they've got some local name servers and they'll handle requests from MIT clients. And this client says, what's ak.xyz.com? And if the local name server doesn't know, it's got to go resolve ak.xyz.com. And so it goes to the authoritative name servers for the .com top level domain. And that authority is run by a company called VeriSign. And they say, oh, you really should be asking the following name server that is the authority for xyz.com. And it comes back and says, oh, you know, ak.xyz.com is really a nickname for a212.g.akamai.net. That's what you really want to resolve. And now the local name server, this is back to the MIT server, it goes and it looks up a212.g.akamai.net. It's told about some authoritative name servers belonging to Akamai that know how to resolve names that end in akamai.net. And the local name server sends a query there. Answer. And here, what Akamai does is it decides which of the many clusters of servers around the world it wants to serve this user from, or this browser's request from. And in our example, when the user's at MIT, it would say, oh, that's a user at MIT. Let's serve the user from the servers that are the cluster of servers on the MIT campus. And so the response comes back, but it's actually not quite done. It's not the IP address of a specific server. It's one last level of delegation to a name server or a set of name servers that are managing the machines on the cluster at MIT. And they know which of those machines have the content for ak.xyz.com, for xyz.com. And in particular, that xyz.com domain was translated to the 212 number in the Akamai name. And they say, oh, okay, at MIT, server number 5 in the cluster has 212's content. And so they send that back. And it goes to the browser. And now, finally, the browser can go and issue a request. Now, I just told you guys, like, round trips are bad, okay? And here we have, in my picture, I've got like 7 or 8 round trips, depending on how you count them. And so a natural question is, I thought Akamai's service was supposed to speed things up. How is that possible if you just made 7 round trips? Does anybody have any idea what the answer to that might be? Oh, still, wait, Charles said it's still SIPB, but I thought it was SIP, S-I-P-B? Okay, I don't know. Francis asks, does Akamai only serve static content? The answer is no, not anymore. And later in this lecture, we'll talk about that. So to a limited extent, the Akamai servers have the ability to generate dynamic content. But more commonly, non-static content that's being generated on the fly or personalized for the user, is still often served through an Akamai server, but it's passed over a tunnel that goes through that server back to the content provider. And we'll see why that is. Johnny has answered correctly. DNS caching, and that's exactly right. So every DNS response that comes from an authoritative name server has a time to live field attached to it. And in this picture, some of the time to live fields are quite long. So the 3 at the top, the time to live for resolving anything VeriSign sends back is probably got a time to live about a day. And that's going to be shared for everybody at MIT. There's only going to need to be one query for ak.xyz.com per day, and that will be cached and shared. Same for the resolution of ak.xyz.com to a212.g.akamai.net. That's probably a day something. So those just aren't ever happening. Now the selected cluster, those TTLs are probably, I don't know what Akamai sets them to today. At one time they were 20 minutes. So you've got a bunch of people at MIT using Akamai services. They're probably not, they're sharing responses and only once every 20 minutes have to make that request. It's only the last one, the low-level DNS servers, that tend to have short TTLs, and that's so that Akamai can respond quickly to flash crowds or to server failures and change the resolution of which specific server a request goes to. Okay, so good answer, Johnny. That's right. The picture is not as bad as it looks. So yes, there may be an extra DNS query. Hopefully that's going to the same. These low-level DNS servers are co-located with the servers that they're managing. So they're in that cluster at MIT. So that extra DNS query is going to the local Akamai cluster, and then you're getting the data from there. And so that hopefully that reduces latency. This stuff was all described in a patent that Tom Layton wrote. He's a professor in the math department with one of his then PhD students, Danny Lewin, who was in the computer science department. And Danny, unfortunately, was one of the victims of 9/11. At the time, he and Tom were the founders and leaders of Akamai. And so they were both very good friends of mine. So let's talk about this deciding which cluster we want to serve an end user from. This really is important because we're trying to reduce latency. And so we have to find a cluster for each particular request that is going to be able to deliver the response as quickly as possible. And now there are a lot of no-brainers. So the MIT decision is a no-brainer. Like, you serve the MIT community, that is the people who are on MIT's network, using the servers that are on that network. That's really easy. And Akamai's tried really hard to put servers into campus networks around the world. But that's not always possible. So sometimes a request will come from a user that's not on a network where we already have a server. And so we have to make a decision. I say we, but I shouldn't, because I retired from Akamai a year ago after 21 years there, part-time. But so forgive me for saying we. But sometimes Akamai has to make a decision. And so the way that's done is through a gigantic active measurement campaign that goes on around the clock to figure out, for each group of users, which of Akamai's clusters are currently seeing the shortest latency. And the way this works is that every night, Akamai compiles a list of all the local resolving name servers that have sent requests for resolution of Akamai names in the last 24 hours. And it sorts them according to which one sent the most requests. And then it takes the top, I don't know how many, 500,000 of those, and it does a trace route to each one of those from maybe 20 places. A trace route is a way of measuring the network path from one location to another. And what it does with these trace routes is that it identifies routers that it calls core points that are straddling the core of the internet and the edge, or the access networks. So in this picture, we have some core point X, some router, where the trace routes from the Akamai clusters to different name servers, 1, 2, 3, and 4, all intersect. And that core point is then the representative of the name servers. And what we'll do is throughout the day, from maybe a dozen different Akamai clusters, ping that core point to ask, okay, which clusters can currently send data to that network, or that core point and the access networks hanging off it with the lowest latency. And ping is a network measurement that just measures round trip, okay? We don't actually measure the latency to end users or to their name servers. We go to this core point and we have no control over what happens after the packets hit the core point. So that's the right place to measure anyway. And so really what Akamai is looking for is latency and packet loss. And it's got a formula that weighs those two and picks the cluster to serve the requests based on, well, and the third thing is cost, which is actually probably most important, but you know, where would we see the least packet loss and the lowest latency? Good. So this 500,000 name servers gets reduced to about 30,000 core points. Turns out that like 7,000 of those account for 95% of the end user load, and maybe 30,000, the whole 30,000 accounts for like over 99% of user load. So that tells you that the granularity of the internet, the number of different places on the internet, places that there's really about 30,000 places around the world on the internet. Okay. So some statistics, and these are a year old, but Akamai has 250,000 servers. They're on 1,700 different networks or ISPs. They're in over 3,000 physical locations in 130 countries. Akamai's services are used by all of the top e-commerce websites, sites like Amazon, all of the top media and entertainment companies, so like all the news organizations like CNN, 16 of the 20 largest banks. The banks are using Akamai in part also for protection against attacks. I don't think we'll spend any time talking about that today. Akamai is also used by all the companies that develop antivirus software. So, you know, I've been talking about how there's money to be made in reducing latency. Most of the bytes, though, are actually in video and software downloads, which are not latency sensitive, and also for that reason are not very profitable because it's not as hard to deliver. But yeah, so to be a full service operation, the content delivery network has to do a good job with video and a good job with software downloads, but it's not really the high margin business. Some daily statistics, Akamai peaks at over 100 terabits per second. Maybe that number is low, maybe it's higher than that now. Every day sees 600 million distinct IPv4 addresses, and today actually even more distinct IPv6 addresses, now that cellular carriers have gone to using IPv6 to assign addresses to the handsets. Right, and every day Akamai serves over 3 trillion requests, which is a big number. If you think about, you know, there's less than 10, maybe less than 9 billion people in the world. So we're looking at 300, 400, 500 requests per person in the world being served by this CDN. So there was a great question earlier about serving static content versus dynamic content. And there is a move underfoot to use content delivery networks for full site delivery so that every single byte goes through that edge server belonging to the CDN before it goes to the end user, or the other way, any byte going from the end user up to the edge server. And 88 of the Alexa top, the last time I checked, 88 of the Alexa top 500 web pages were being served by Akamai. So when you type, you know, www. Well, I don't know, I'm making something up, but mybank.com, you're probably actually connecting to an Akamai server, not to a server that's owned by that bank. And the reason for this is sort of this, it's this bizarre thing, but it has to do with TCP session establishment and latency and round trips. So it's called the split TCP and TLS optimization. The idea is that you saw that there's this three-way handshake that's needed to establish a new TCP connection. Well, how long that takes depends on the latency between the client and the server. So it'd be awfully nice if that handshake could happen with a nearby server. That's the nearby Akamai server. So even though you really want to connect to your bank, you open up a TCP connection to the Akamai server, which has already in advance opened up a persistent TCP connection back to the origin server belonging to the bank. And that connection is ready for data to be sent. The handshake's already been done. And the same is true also of the TLS handshake. That all those round trips needed to exchange keys, they're done with the edge server. The edge server already has a TLS connection open with the origin server. Another interesting thing you can do is once you've got this intermediary, this front end edge server, you can do wacky things like build an overlay network, which Akamai does, and route the packets back to the origin server through another Akamai server somewhere else. Now, most of the time, this probably only makes things worse. But if there's any problem on the default path that's provided by the internet between the edge server and the origin server, you might be able to avoid it by routing around it, taking a detour. It turns out it's a dirty little secret, but in the wide area, the paths that packets take in the internet over medium and long distances, the network protocols that select those paths do not take performance into account, period. It's just not, there's not even possible. There's no fields in the protocol packets that would tell you what the performance is. It's done entirely to minimize cost, okay? And so it's not surprising that sometimes you're getting the route that the network providers want you to use because it's cheap, but the performance is poor. And so sometimes using these alternate routes can help. Now, another motivation for doing this is that you could block attack traffic at the edge server if you can identify it. And so that's in the case of banks, that's another reason why they've outsourced delivery of their site. But I shouldn't say outsourced. They've moved to full site delivery, which means the bytes go through an edge server, also because all the requests have to, and they can be blocked if they're bad. One of the consequences of this architecture is that Akamai has to operate the DNS for the top level domain for the customer, like www.mybank.com. Akamai now resolves that, and Akamai holds their private keys for their TLS public certificates. So Akamai is in the position of acting as an imposter that cannot be detected because they've been given all the legitimate credentials. Okay, so we're going to move on to the last part of the talk, and that is all the things we've talked about so far are sort of, you're given an internet, what are all the little things you can do to try to make things work faster? But another approach would be to let's just make the darn network faster. And I'm going to talk a little bit about a project I've been working on for the last 5 years called the Internet at the Speed of Light. And here's a little experiment we did. This was with a graduate student who is he's now a professor at ETH Zurich, Ankit Singla, but at the time he was a PhD student at the University of Illinois in my hometown of Urbana, the University of Illinois being in Urbana-Champaign. And what he did was he went and fetched 20 kilobytes from a website called theoatmeal.com, which happens to be hosted in Oregon somewhere. I don't know why. He also sent a ping to that web server, and that just measures round trip latency. It's sending one small packet and getting a response. So to fetch 20 kilobytes, which is a very tiny amount of data, took 430 milliseconds. To send a ping took 55 milliseconds. Urbana to Portland round trip distance is 5,700 kilometers. And at the speed of light in a vacuum, that would be 19 milliseconds. And so the time it took to get 20 kilobytes of that web page, which really should not be much more than 19 milliseconds in a perfect world, was 23 times more. And even the time to do the ping, just sending one packet, one round trip, was 3 times more. So 3 times more. So, but this is a great rule of thumb, by the way. The time to, in the wide area, as long as you're on a wired network, the time to send a packet over medium or long distance is generally about 3 times what it takes light to make a round trip. Okay, and the reason for that is, number one, in the wide area, the packets are generally traveling over optical fiber, and optical fiber, the speed of light is only it's 1.5 times slower than in light in a vacuum. Also, the fibers don't always take straight paths, and the network routing protocols don't always pick the shortest path anyway. Okay, so this factor of 3 is sort of pervasive. So that was one little experiment, but Ankit repeated this experiment from using a bunch of servers that had been deployed for research purposes in 186 locations around the world. He downloaded the first 20 kilobytes from 500 the 500 most popular websites in each of 103 different countries. And this, by the way, was done a bit before the movement to full site delivery had really taken off. So he was touching a lot of servers at a lot of different distances, 28,000 different websites. And the median time to fetch that 20 kilobytes was 35 times one round trip at the speed of light. Okay, so you could view this as, that's terrible. The internet is 35 times slower than it has to be. Or you could say, wow, as a researcher, I'm going to be able to work on this problem for years and keep reporting progress. So it's kind of a mixed bag. But 35 times, that's embarrassing, okay? And you might ask, well, okay, why is it so slow? Where's that 35 coming from, okay? We'll get to that, but it's a combination of round trips, and then it's this factor of 3. But at this point, some people will stop and say, wait a minute, isn't the network fast enough already? Like, I can already watch videos. Well, videos don't require super low latency, but there are indeed contexts in which latency really matters. And one of them that we've seen already is musical collaboration, okay? So, you know, Zoom is some crazy thing where you guys are all at MIT, but you're connecting through some Zoom server and we don't even know where it is. And I'm in North Carolina, and either the rest of the class is remarkably bad at keeping the beat, and that's why you were 3 seconds behind me from what I heard, or we just got tremendous network latency, okay? But here's another. Does anybody know what this is? These are people who want low latency. Surely among this class, there are a few people who would appreciate the setting shown here. Anybody know what this is? Yeah, it's a LAN party. It's a gaming tournament, right? If you're going to play games, the latency really matters a lot. And you know the best way to reduce latency is to be in the same room. You guys, my son just left, but he was in here just now playing some game with Oculus Rift, and my kids are merciless to me. When the network is slow, when they're trying to play games and it lags, they say, "Dad, our Wi-Fi sucks." And I'm like, guys, you're not on Wi-Fi. Your machine has cable directly into a port on the router. You're not even going through a switch. And they're like, okay, fine, Dad. Akamai sucks. I'm like, okay, well, you know, what can you do? But yeah, the gaming really matters. By the way, latency isn't the only determinant, because skill actually matters in these games too. I remember when my son was about 12, I was trying to play a game called Halo with him, Halo 2, I don't know. And he kept killing me. I said, Peter, I think the game's broken because I'm not even hearing the gunshots and you keep killing me. He said, Dad, I don't need a gun to kill you. Okay. How about this? Here's a weird thing. You know, it turns out that the human sensitivity to external stimulus is not perfect. And experiments have shown that if you click on something with your mouse and the response comes up on the screen in 30 milliseconds versus 0 milliseconds, you can't tell the difference. Okay, so that 30 milliseconds is at 30 frames per second. So that's be one frame at 30 milliseconds, or 2 frames, sorry, at 33 hertz, or 2 frames at 66 hertz, right? So if you could send a request, generate the response, and send it back to a client within 30 milliseconds in an interactive application, as far as the client knows, that's as fast as if it happened locally, or just in an ideal world, it just happened instantaneously. But at the speed of light, 30 milliseconds takes you a long way. So you could have one server in North Dakota that's within 30 milliseconds of almost the entire United States. So not Hawaii or Guam, but maybe little parts of Alaska, the Aleutians, but everything else is within 30 milliseconds round trip of North Dakota. That's kind of a cool idea. 7 data centers around the world would be enough to be within 30 milliseconds of everybody. So I'll skip that. Why are we so far from the speed of light though? So we saw this factor of 35. The first reason, and you saw this, is that we do a lot of handshaking. There's the TCP 3-way handshake. After that's done, the server's not allowed to blast data at a client as fast as it can. The two of them slowly negotiate the rate that can be sustained. So to send even 20 kilobytes, which gets maybe broken down into, I don't know, 10 or 15 packets, there's a few round trips that go. The server doesn't just send all 15 packets at once. And then we have TLS. And how to improve these things, I'm not going to talk about anymore, except that the key idea is caching TCP sessions, so that a new session can be opened by providing a TCP cookie or credential, or caching TLS sessions the same way. And these are things that Google has been pushing. And also there are new protocols meant to replace TCP, like QUIC, that also aim to reduce number of round trips. So I mentioned that there's this inflation factor of 3.2 for one round trip. This means this factor of 35 comes up because basically we had the factor of 3.2 and it took 11 round trips in order to deliver 20 kilobytes. So the last part of the talk is a little more speculative, and it's maybe the most fun. It's, could we build a speed of light internet, a network that runs really close to the speed of light, even over medium and long distances? And it turns out that the answer to this is, well, if it really mattered to you enough, it can be done. And we know this because high frequency traders have built a series of extremely low latency networks connecting financial data centers in New York and Chicago. And the first few of these networks were based on optical fiber. So here the darker red and the green networks were a pair of fiber networks. And the darker red one was established first. And these networks are used to take advantage of momentary differences in price between commodities in Chicago and New York. And the idea is that the trader who can get their order in first can make a quick profit. And it's a winner take all type of thing. If you get there first, you make a profit, and otherwise you don't make a profit. And basically this is a draconian competition. So when the second network went in, the green one, and it was 1.4 milliseconds faster the red one lost all its business because you couldn't defeat any trader who was using the green one. And then the next network that came in, the McKay Brothers network, switched from using fiber to point-to-point microwave relay stations, separated at distances of like, I don't know, 50 kilometers or something. And there have now been a series of improvements where they're just straightening out the path and trying to eliminate towers. So you have fewer intermediate relays. And they're up to 99% of the speed of light to send data from New York to Chicago. And it turns out McKay Brothers has very graciously given my research team access to their network on Saturdays, because on Saturdays, all the world financial markets are closed. And so we've been doing a lot of experiments trying to understand how do these networks behave at the bleeding edge, and learning things about what kind of weather disrupts these networks. And there's some weird phenomenon here you never would think of. Like, once you make your network path really straight, you have to be careful that when you send data from one tower to the next, it doesn't pass on from there and then interfere with the receptions at the tower after that. So there's a lot of very careful tuning of how much power is used in each hop. So if you want to build a network like this, one of the things you have to do is figure out, okay, which towers can talk to each other. And there's a standard formula that you can use that takes into account the height of the towers, the distance between the towers, the frequency that you're going to transmit at, and the curvature of the Earth. And it says that there's this zone called the Fresnel zone between the two antennas that has to clear any obstacles if you are to be able to successfully transmit. But this stuff is really well known and the models work really well. So it's possible to ask for any two towers, okay, could they communicate and how much power would it take and at what frequency? So we set out to ask the question of, could we build a speed of light network for the entire United States? And there's a lot of data for the United States showing where every single cell tower in the US is. So we started out with locations of all the cell towers. And also we have locations of all the people, like where are the major population centers? So we asked, what if we had the top 200 population centers in the US? And we want to connect them, okay? And we're going to build a network that its capacity, we have to somehow model how much traffic would go from New York to Chicago or Chicago to St. Louis or whatever. And so we used a common and very crude model called the gravity model that says the traffic between two cities is proportional to the product of their populations. Turns out you can tweak this model in many ways, make it decrease as a function of distance. There's a lot of things you could do. It doesn't seem to matter too much. We got terrain data from NASA, so we knew where every mountain and hill was. We also got a map of all the fiber in the US, and this was produced by a different group of researchers as part of their Intertubes project. So we needed to know in some places we're only using existing towers, we're not going to build new ones. In some places we might have to fall back to fiber, but not too often. And so the result is, here's an example network that has 100 gigabits per second aggregate capacity. That's not a lot. So microwave links are going to have much lower capacity than fiber, but they make up for that by being 1.5 times faster, even if the fiber is on the exact same line of sight route. In some places, we had to find parallel towers so we could get higher capacity. So you see some double and triple capacity planning. And here we also, in a very small number of places, like somewhere in Texas to somewhere in, I don't know what state that is, Colorado? Yeah, I don't know. Somewhere in there, we had to run some fiber, and somewhere across Florida, we had to run some fiber. But this network, and it's a plan, it hasn't been built, would provide you pretty close to speed of light latency. So the 50th percentile between any pair of population centers is 1.05 times the speed of light. That's the slowdown. And the 99th percentile is only 1.38. And these numbers are weighted according to the gravity traffic matrix. Okay, so let's talk about some new and even more exotic ideas. So you guys may have heard about Elon Musk's SpaceX Starlink internet constellation. My stepson works there, and he works on designing those satellites. For many years, we've used satellites in geosynchronous orbit for a lot of purposes, like delivering video from remote locations, live video of, I don't know, a sports event or something. But geosynchronous orbit, which is an orbit that's at just the right altitude that the satellite will stay over the equator at exactly the same spot, is too high for low latency. It's like 20,000 miles, and it's 240 milliseconds round trip, and that's way too much. You saw the round trip to Chicago is 9 milliseconds, or 9 or 10, right? So 240 is too much. But the new Starlink low Earth orbit satellite network, here the round trip just to get up and down, you're talking about 1,000 kilometers, maybe a little less. That's like 7 or 8 milliseconds. So yes, there's a penalty for getting up, but the Starlink satellites today, this doesn't work. But ultimately, they're meant to have laser communications in space from satellite to satellite. And so over really long distances, like over oceans, those may be able to beat fiber. This is what the Starlink constellation looks like. So you have a bunch of different low Earth orbit satellites, and they don't actually cover the North and South Pole. But the hope is that at any given time, kind of anywhere else in the world, it should be possible to send a signal up to a Starlink satellite or receive a signal from one. And perhaps someday in the near future, the satellites will also be able to transmit signals amongst themselves. Today, they have to send data down to a base station somewhere, which then routes it on fiber and then back up to the satellite nearest to the receiver. I want to tell you some experiments we did to try to uncover tricks that the financial traders were using to get data across oceans as fast as possible. So here's a little graph. So this is latency between Washington, D.C. and Frankfurt. And on the x-axis, we have milliseconds, and we've labeled a couple of interesting points. So if we do the experiment over the public internet, the round trip latency is like 47 milliseconds. If we rent a fiber network that is used by financial traders called Hibernia, it takes 36 milliseconds. If we had a fiber, the fastest it could possibly be in fiber, if we had a straight fiber from Washington, D.C. across the ocean to Frankfurt in a straight line, would be about 33 milliseconds. And then at the speed of light, so fiber is 1.5 times slower, that's 22 milliseconds. And looking at constellations with different numbers of satellites, you can see that once you got up to, so these are 100 satellites, 225 satellites, 400 satellites. So what we're trying to show is, as you increase the number of satellites, so you're more likely to find a straight satellite to satellite path from Washington, D.C. to Frankfurt, how fast would it be? And the reason we have a y-axis here is that you can't describe that with one number because the satellites are moving, and at different times they'll use different paths. And so sometimes you'll get a better path than other times, although as you add more and more satellites, it's more likely that you'll have a good path available most of the time. And so you can see here that with 30 squared, 40 squared, or 50 squared satellites, you can almost always beat the fiber latency. So you can expect that the traders are going to do this. Another thing you could do is use airplanes. So we looked at, there's databases that show where every commercial airplane is at any given instant in time. And so we looked at this data and we asked, what if you could do line of sight radio transmissions between airplanes? Could you, how fast would that be? And how often would you be able to find a path between financial centers? And it turns out, well, there's a lot of air traffic between financial centers. So it's almost always the case, or maybe always the case, between New York and London or Shanghai and Frankfurt, that you can get paths where the inflation of speed of light is less than 1%, going hop to hop using airplanes. Okay, so I'm going to end here with an inspirational quote, which I'm not going to actually necessarily read the whole thing, but it's a warning to people who have taken 6172, and that is, you can go too far trying to optimize performance. And this is a hilarious quote about the first computer programmer, perhaps, who became obsessed with making his code run faster. This is in Richard Feynman's book, Surely You're Joking, Mr. Feynman, about this man named Frankel, who was supposed to be supervising the computer systems. And instead, he became obsessed with making his arctangent code run faster. And don't let this happen to you. There is also a point when your performance is good enough and it's time to move on. And I want to thank you guys this has been a great audience. I usually get a lot more heckling. I hadn't realized that Zoom it's a completely different medium. But at this point, I could answer questions, or I don't know what you guys do to finish off your class.
Yeah, we can take some questions. Do you want to stop the screen share and then we can chat with students for a bit?
Yeah,